All right, so to get into our next topic, which is bagging and random forests, I want to do a little bit of a sidebar on some basic statistics terminology that we'll want to refer to, and a little bit about the Bootstrap from statistics. It's kind of interesting in its own right, but we'll kind of hustle through these slides, but at least we'll get a flavor, and we'll get what we need to go to the next step for bagging. So bias and variance. Let's go back. Remember a couple weeks ago, we defined statistics. A statistic was an arbitrary function of data. So a parameter is an arbitrary function of a probability distribution. So if P is a distribution, we often want to estimate some characteristic of the distribution, like its mean, or its median, or its kurtosis, or skew, or maybe you want to figure out the full cumulative distribution function or something. All of these things are considered parameters of the distribution. Any function of the distribution, that's a parameter in a very abstract sense. So you could write that as mu of P, where P is the distribution of interest. And now, first question, is mu random if mu is a parameter? Would you consider mu a random variable or a random value? Seeing some no's. No. P is just a probability distribution. You could think of that as a density function or something. So some characteristic of a density function is not random. It's just kind of a mathematical thing. So for instance, you want to find the mean of something that has a density f. It's just this integral. It's a number. There's nothing random to a parameter. All right. On the other hand, if you get some data, dm, you define a statistic as any function of the data, as we have. And you could have a statistic that's a point estimator of a parameter. That's what we talked about last week. So of course, statistics are random. They're functions of data, which is random. OK. Good. So the mean of a sample is a statistic. The median, statistic. Sample variance. Have you seen sample variance? A way to estimate the variance of the distribution that you are sampling from. The sample variance is an unbiased estimator. We'll see what that means in a bit. This should be familiar, though, from statistics, basic statistics. A data histogram could be a statistic. Empirical distribution function, a confidence interval. All these things are statistics as they are functions of the data. All right. So I mentioned statistics again because statistics, since they are random, they have themselves a probability distribution. Right? So we started with the distribution P. Right? We started with P, distribution P, and then went through some slides, and then we said, OK, now let's suppose we have a sample from P. That's some data dn, our data set. And then we introduce a statistic, a function of the data, and that's random. So this statistic has its own distribution, and that's called a sampling distribution. And often, we want to know characteristics of the sampling distribution. Of the statistic? So what characteristics might we want to know about a particular statistic? Suppose a point estimator. Right? Suppose we're trying to estimate mu, the mean of a probability distribution P. And someone proposes a point estimator, the empirical mean of the data. Let's call that x bar. X bar is random, because it's a function of the data. So it has its own distribution, called the sampling distribution. What characteristics of that distribution might you be interested in knowing?
Mean variance.
Yeah, maybe the mean and variance of the sampling distribution. Great. So the reason you might want to know the mean, because you hope that the statistic actually estimates the parameter you're going for. So you're hoping that the mean of your statistic is, the expected value of your statistic is at least close to the parameter you're trying to estimate. What about variance? Why would you want to know the variance? Why is the variance of the statistic interesting?
So we can know how good of an estimate it is of
Yeah, how good of an estimate is it of the parameter you're trying to estimate? If a statistic has a very high variance every time you got a new batch of data, it would change quite a lot. The actual parameter you're trying to estimate, of course, stays the same. And so that indicates you're having potentially a large error. And roughly speaking, the scale of the error of your statistic is going to be the scale of the standard deviation of the distribution of that statistic plus any potential bias, which we'll get to in a second. All right. Great. So a term we'll introduce, the standard deviation of the sampling distribution for a statistic. It's called the standard error. You've probably heard standard error before. We could precisely define it as it's the standard deviation of the distribution of your statistic. All right. So is standard error random? Ooh, good question. I see some no's, but I see some yeses. All right. So the standard error is a characteristic of a distribution. It's the standard deviation of the distribution of the statistic. So it's a parameter of a distribution. So the standard error is not random. Okay. So some more terminology, bias and variance. So this is relevant to point estimation scenario. Mu is a parameter. Let mu hat be an estimator of mu. So mu hat is our statistic. So mu hat, we've defined it. It's a function of the data, but for short, we'll just write mu hat, and the data set will be assumed. Similarly, the parameter mu, you could think of it as a function of a distribution, but let's just assume we're fixing a distribution p. So mu and mu hat are our parameter and the point estimator for that parameter. So you might ask, we will define two notions. One is the bias of the estimator, and the other is the variance. So the bias of the estimator mu hat is the difference between the expected value of mu hat and mu, which is what you're actually trying to estimate. So unbiased is that if you found mu hat for lots of different samples of data, and you took their average, that average would converge to the expected value of mu hat by the law of large numbers. If that differs from mu, what you're trying to estimate, then that's called bias, and the gap is the gap between expected value of mu hat and mu is called the bias. The variance this is the standard formula for variance, definition of variance of our statistic mu hat. Standard deviation is, of course, square root of variance. Just a little recap. So we say an estimator is unbiased if the bias is 0. So the expected value of your estimator is equal to what you're trying to estimate. And just again, we come back to the question of what's random and what's not. And the bias and the variance, again, are not random. Bias and variance are kind of characteristics of the sampling distribution of your statistic. So they don't vary from sample to sample. Is that clear? So if you take a sample, you compute a mu hat, it won't exactly equal mu. The difference will be mu hat minus mu. That's a residual. It's a gap. It's an error. But the expected value of mu hat is not random. The error is random, but the expected value of the difference is not. All right. So suppose we want to get error bars on our estimate. We want to find the standard deviation of our statistic. So we would want to find the variance, and then you could take the standard deviation, the square root of that. So you need an estimate of mu hat and mu hat squared if we go back to our definition of variance. And but how do we come up with those estimates? And our approach here is going to start with a thought experiment. Let's suppose that we had not just one sample, D, from which we got a mu hat, but we had a whole bunch of samples. Suppose we had B independent samples. Each sample is of size n, and we have B of them. All right? So there's a distribution. We drew endpoints from it. One sample. That's D1. Then we again drew endpoints. That's another sample, D2. And then we did that B times. All right? So we have B independent samples, each of size n. All right? For each of these samples, we can compute our statistic. Mu hat on the first sample, mu hat on the second, mu hat on the third b times. All right. Each of those mu hats you should think of as a sample, as a draw from the sampling distribution of the statistic mu hat. We could, for instance, make a histogram of all the mu hats that we got from each of the b samples. And that would be an estimate of the distribution of the statistic. It would be an estimate of the sampling distribution. From that estimate, we could perhaps derive other quantities of interest. You could estimate the standard deviation, the variance, the kurtosis, whatever. So the idea is that you can, if you allowed yourself b independent samples, then you can do a lot to estimate the sampling distribution of mu hat. So for example, if you wanted to estimate the expected value of mu hat, maybe you don't know if it's biased or not. You want to estimate the expected value of mu hat, you could look at the average of the mu hats you got across your b samples. Right? You want to estimate the expected kind of the second moment, you could do the same. The empirical average of the square of mu hat. And then you could plug those things in, and here would give you an estimate of the variance of mu hat. How did you do it? You got a bunch of samples of mu hat, and you computed kind of the empirical variance. Yeah?
I was a little lost before. Can you explain again why variance is not considered random?
OK. So why is variance not considered random? Well, it's a characteristic of a distribution. So let's start in the simplest case. We start with the distribution, Gaussian with mean 0 and variance 1.
Right, but the variance specifically of this sample, why is that not good?
Oh, great. The variance of a sample is absolutely random. The variance of a distribution is not random. OK, so let's see. So mu can be a function of a distribution, such as the variance. Any distribution, you could solve an integral and compute its variance. OK, same for the mean. Now we come up with. Now we want to be able to estimate those parameters, the mean and variance of a distribution, given some data. So we create kind of a parallel function, which doesn't work on distributions. It works on data sets. That's mu hat. So whereas to figure out mu, the mean of a distribution, you might do an integral. To figure out the mu hat for a sample, it's like an average. And so mu hat will correspond to mu. They're different functions of different things. Mu hat is going to be random because you're applying it to random data. All right. Now, I was also saying that the variance of mu hat is not random. Why do I say that? The variance of mu hat is not random because, in some sense, we're kind of integrating out over all samples that we can get. So to think about the distribution of mu hat, I think the example we gave is a good one. You can think about for every random draw of data D, you get a different mu hat. All right? Different mu hat, different mu hat, different mu hat. So the mu hat has a distribution to it. That distribution has a variance. The distribution doesn't change. What you keep, each mu hat is a sample from that distribution.
Sure, but isn't variance also a function of the data points?
OK, so yes, mu hat could be an empirical variance of the data points. That's right. Let's assume it is. So mu hat is, yes, could be defined as the variance of a set of data. And that is random. That's right. Mu hat is random. But the variance of mu hat, so it's the variance of the variance estimator, is not random. OK. So yes, a little confusing, but yeah. All right. So why do we care about estimating variance? I kind of pointed that out already. You could get confidence intervals on variables, values. OK. So here's kind of an example of what I was explaining. Was imagine now that there is some parameter alpha of a distribution p, and for some unknown p, and then someone comes up with a point estimator alpha hat that's supposed to do a good job at estimating alpha. And we'll, for instance, evaluate it on samples of size 100 from p. All right? And so we can come up with alpha hat. It'll just be a number in this case, because alpha is a number. But suppose we want to get some standard errors on that alpha. How do we know how good it is? What would we have to know to figure out how big the standard errors should be? We kind of want to estimate the standard deviation of the sampling distribution of alpha hat. That'll tell us roughly how big the errors are of alpha hat estimating alpha, assuming unbiased. All right. OK, so one way to get the distribution of alpha hat would be to simulate if you had access to the distribution p. So that's what's going on here. We've carried out the operation I described. So this would be in this case, b was 1,000. So we sampled a data set of size 100 from p, and we got an alpha hat. And then we did it again, a new data set of size 100, and we got another alpha hat. And again, and we did this 1,000 times, and we got 1,000 alpha hats, one for each of 1,000 draws from the data generating distribution. How big were each of those draws? 100. All right. We histogrammed all the alpha hats, and we get this. All right. So this is an empirical estimate of the sampling distribution of alpha hat. So roughly speaking, our confidence interval might be from here to here, right? Captures most of the bulk of that distribution. That's the idea of what we're looking for with a confidence interval. In this case, the true value is the line in the middle. All right, this is all well and good, and I think it does a good job. I hope it does a good job of kind of intuitively explaining this notion of a sampling distribution. But we're probably not going to want to do this in practice. So in practice, you will have one sample from your distribution. It's of size 100. If you want to do this type of thing, you're going to have to break it up into groups. Maybe you can break it up into groups of 10, and then you're estimating getting alpha hat from each of these small groups, and then at least you'll have a distribution. But this is a bad trade-off. You'd rather use all your data to get your estimate, and then somehow or another figure out your confidence intervals. Okay. Okay. So that motivates this notion of the bootstrap. So a bootstrap sample has a very specific definition. So the bootstrap sample assumes we've already gotten our initial sample, call it dn. From that sample, we sample again. We sample from the sample. A bootstrap is a sample from the sample. And we sample from the sample endpoints with replacement. All right, if we sampled endpoints without replacement, we just get dn back. OK, so that's not interesting. But we sample n times from that set. So you should picture a bag full of x1 through xn. We reach in and take one out. We write it down, and we put it back. We reach in again, take it out, write it down, put it back. We do that n times, where n is the size of the sample. OK. So a few things. We're, of course, going to get repeats. And we're, of course, going to find things that don't show up at all in our bootstrap sample. And that's fine. Can we compute the probability? Let's quickly compute the probability that a particular example never shows up. How about? So how do you want to do this? We have n independent draws.
How many items do you draw?
How many times do you draw?
No, how many items?
You draw one at a time. You draw one, you put it back, and you repeat n times. Yeah? All right, so every time we reach in, let's consider a particular object. Let's suppose x1 for simplicity. So what's the probability we don't get x1 in the first draw? Yeah, n minus 1 by n, which is 1 minus 1 over n. Yeah, OK. What's the probability that we don't get it in the second draw? The same, and they're independent. So what's the probability we don't get it in any of the n draws? OK. What's this equal to? Yes, it's e-ish. It's e-ish. That's right. It's e to the minus 1. That's right. Which is like a third. All right. So that's a pretty high probability. That's the probability of any particular element not being selected in a bootstrap sample. OK. So we'll definitely have some diversity in the sample. We'll have some repeats. We'll have plenty of repeats and some missings. Each bootstrap sample will look quite different. All right. So here's the idea of the bootstrap. Remember when we were taking independent samples, b of them, all of the same size? Bootstrap, you do the same thing, but they're bootstrap samples from the original sample. All right. So here, we start with some original data. And then we take a bootstrap sample. Of course, it's of size 3. Bootstrap samples are always the same size as the original data set. Here's another bootstrap sample, another. So in the first one, we got 3 twice and don't have 2 at all. Here we have all of the inputs. And here, 3 is missing. We have 2 twice and 1 once. For each of these bootstrap samples, we compute alpha hat. All right. And then we can do a histogram of alpha hat. That would be kind of the sampling distribution of alpha hat from the distribution defined by the original data, like the empirical distribution of the original data. That would be what we're estimating with all these bootstrap alpha hats. So a bootstrap method is when you simulate having B independent samples by using B bootstrap samples. It's like just a swap and replacement. You mentally conceptualize what you want to do as though you had B independent samples from the distribution. But at the last minute, you substitute in bootstrap samples instead of independent samples. That's a bootstrap method. What's amazing is that the results often come out very similar. And using bootstrap samples instead of truly independent samples gives you a very good approximation. So here's our B bootstrap samples. You compute your function, your statistic on each of the bootstrap samples, and then you can aggregate them in some way. You can work with them as though they were statistics on independent data sets. All right. So any questions? We're about to look at some results here. All right. So let's look at what happens when we do the bootstrap. So same setup. We had 1,000 independent samples of size 100 each. We computed alpha on each of the 1,000 independent samples. And then we do the same thing with 1,000 bootstrap samples. And here are the 2 histograms we get for alpha hat. This is the truly independent samples, and these are the bootstrap samples. And they're quite close. On the right, we have a, what is this, stem and whisker? Box plot, thank you. Box plot of the values of alpha for the true and the bootstrap. And yeah, you can see, so these kind of the blue and the yellow regions are kind of like confidence intervals for the, they can be interpreted as confidence intervals for alpha hat for the parameter we're estimating. And they're quite close. So this is the bootstrap method. The theory for bootstrap is quite difficult. So it's pretty advanced statistics to prove a lot of, to make this rigorous. So it's not something I can go through, but it's quite a workhorse in modern statistics to come up with your standard errors for different estimators. Estimators alpha hat, for instance, where it's too hard to come up with a closed form distribution or something like that. Yeah.
What's the typical value of b used? Like how many times you?
I mean, usually 1,000 would not be unreasonable. It's always a little bit of how long are you willing to wait. I mean, you could see, I mean, it's kind of the same question of how many points do you need to get a good histogram estimator, or how many good points do you need to estimate a variance or a mean. So it's kind of the same. It's the same question that you would ask when you're trying to estimate any parameter of a distribution. How big does your sample need to be to get a good estimate of it?
But the minimum for that is like typically under it, like it's 30 to 40, right?
Yeah, I would.
The minimum, absolute minimum.
Yeah, I mean, I would go larger. This is computer simulation, so you should be able to generate, yeah, thousands, tens of thousands. Yeah. I mean, you could keep increasing it and seeing when your values kind of level off, and sorts of thing. So what happens when you change 1,000 to 100,000? What happens to this blue histogram?
Just becomes more granular.
Yeah, it becomes more smooth. So you can kind of use your, you could use your intuition on when, and for these estimates, the values would stop changing that much at a certain point. So, all right, so we're going to use it. We're going to use that type of sampling to talk about bagging.